Hi, and thanks for joining us on this revision zone video, which looks at the calculations for Hess cycles and follows on from part 5, which just looks at the construction. So we'll be looking at the calculation of formation and combustion. We're going to start off with formation first and then follow on to enthalpy of combustion calculations. Now, we are going to start off with a very familiar reaction that we looked in the previous video. This is reduction of ethene, and we're going to look at calculating the enthalpy of reaction for this process. Now, I have, prior to the video, I've written up the enthalpy of formations. You will be given these in the exam. They don't tend to ask you to look for them in a data booklet. They're more focused on, can you do the calculation and can you apply them in the right place? What you will notice here that I haven't put the enthalpy formation for hydrogen. It's not required. You should know that the enthalpy of formation for any given element or uncombined element is 0, and therefore it will not be given to you in the question. So if you're ever doing an exam question, don't be confused by that. Now, let's get stuck straight in. Now, I want to construct the Hess cycle first. So in order to do that, I'm going to write down the elements that are in the top. Now here, I've got carbon, hydrogen, gas, and they're in their constituent. They are the constituent elements, and they are as they are found in standard states conditions. I'm going to have arrows going up this time because I am going to be forming the components in the above equation. Like I said, we don't have the enthalpy formation of hydrogen. I'm going to write down that this first blue arrow on the left is delta H1, and the one on the right is delta H2. Now, what I've done for simplicity is I've written delta H1 and delta H2 rather than writing out all the long format, if you like, of delta H formation of ethene and delta H formation of ethane, respectively. Now, but what I will do underneath is I'll say, well, delta H1 is equal to the enthalpy of formation of ethene. Messy, I'm sorry. Right, plus the enthalpy of formation of hydrogen gas. Now we know this is 0, so we didn't really have a need to write it, but we will anyway. Delta H2 is equal to just the enthalpy of formation of ethane. Now we have these values up there, so we'll move over to the calculation now. Now, before I do that, I just need to make sure I know which direction I'm going in. So I start here, I finish here. So I want an arrow going across. I go down, across, and up, which takes me to the final point. Now that shows that this arrow is going down. It's going against delta H1. So delta H1 is minus. It's going along the same enthalpy as delta H2. So this will be plus. So if I move over to my calculation of enthalpy of reaction, stick my R in there, is equal to delta H2 minus delta H1. And you'll see that this format repeats itself with enthalpy of formation Hess cycles. I have the values at the top. My delta H2 is the enthalpy of formation of ethane, which is minus 84.7. That 4 a bit clearer. Minus, always put your signs in, even if they're positive, always include them. It's very important. The signs give you a direction. So even writing a positive there tells you something about that enthalpy. Let's do it that way. Therefore, our final answer, and always show all the steps in your calculation. That way, if you do make a mistake, as you'll see in later or latter questions, there'll be a few more steps within the calculation because we're using more numbers. This comes to a minus 137.1 kilojoules per mole. Now, I'm not going to do this for all the calculations below, but sometimes in exam questions, they will ask you for an appropriate significant figure. Always keep an eye on that. That's where some students lose unnecessary marks. AQA, to my knowledge, typically ask you to write answers, or they expect you to write answers which are to an appropriate accuracy. And the way to do that is, well, say, in my data, I've been given values to 3 significant figures, so I really can't give this value. Whoops, let's do that again. More than 3 significant figures. So I should just write minus 137 kilojoules per mole. So that gives us the value of this enthalpy of reaction. Now, that's the first example. So let's now move on to the second example. So this is a slightly different example. And the equation, the enthalpy of reaction that we're trying to work out for is this one here. And this one does require balance. We need a 3 in front of the carbon dioxide and a 2 in front of the iron. So we just need to make sure we've had this equation completely balanced. Let's construct our Hess cycle again. Now again, I need to write the elements at the bottom, or the constituent elements, in order to do that. So let's start with that. And in this case, we've got iron, which is solid. Got carbon, which is solid. I didn't mention above, but this I have mentioned in previous videos, that carbon is the graphite form, or the form of graphite. Oxygen, which is O2 gas. Now these are our elements that we require to make the above components. We need to make sure it's balanced, of course, with the above. So I need 2 ions, and we're only comparing to one side of the equation. I won't want to compare both sides. I don't want to write 4 here at the bottom. It's only 2, so I'm comparing to one side. As long as the top one's balanced, nothing will go wrong. 3 carbons and 6 oxygen, so I need a 3 in front of that O2 there. Now our arrows will go up, and on both sides I'm going to put delta H1 here, assuming standard conditions and states, delta H2, and so on. Like I said before, delta H1 represents the enthalpy of formations of both these substances, and the delta H2 will represent the enthalpy of formation of both these substances. Now you may have noticed that this is an element, so therefore we already know the enthalpy of formation of iron is 0. Now a lot of students tend to not realize this in exam situations, maybe because they're nervous or panic or just don't read the question properly, and they won't give you that value within the question. So don't get puzzled, or don't be puzzled by the fact that that enthalpy is not given. The reason they haven't given you is because it's 0. Now just below, I'm going to write down what delta H1 is and delta H2. So delta H1 is equal to, now I only have 1 mole of iron 3 oxide, so it's the enthalpy of formation of iron 3 oxide, solid, plus, now we have 3 lots of the enthalpy of formation of carbon monoxide. So I've put a multiplication of 3 in front of that term. I'm going to close that bracket. So that's what my delta H1 is equal to. My delta H2, on the other hand, now we know iron is 0, so I'm going to completely ignore that. We don't need to put that in. And it's 2 lots of the 1 mole iron, so 2 times 0 will be 0, so it has no effect, obviously. 3 times the enthalpy of formation of carbon dioxide gas. So now we know that, let's get on and work out the enthalpy of reaction for this equation. So my enthalpy of reaction is equal to, now we need to go back to our Hess cycle and put a dot where we want to start, dot where we want to finish. We're going by an alternative route, so down, across, and up. missed that dot a little bit there. We can see that again, we're going in the opposite direction of delta H1, so that's a minus, and we're going in the same direction as delta H2, so that's a plus. So over here, switch back to black, okay, it's still delta H2 minus delta H1, and you should start to see a pattern with the enthalpy of formation calculations or Hess cycles. It's always this delta H2, the one on the product side, minus the enthalpy of formations, or the sum of enthalpy of formations for the reactants. It's always this same routine. So let's go ahead and write those numbers. Now we have 3 times the minus 394, which is for the carbon dioxide. This is part of delta H2. Let's put the enthalpy of reaction here, minus, now we've ignored iron, remember that we're only doing this one here. We're now going to go on delta H1, so we need to now incorporate that. So minus, big bracket if you like, 1 mole of iron 3 oxide, so it's just 1 times the minus 824, plus 3 lots of my carbon monoxide, which is minus 110, 410. I always advise that you always show every step of your calculation in an exam situation. A lot of students will almost just skip to the final answer, and if you've made an error, you will lose marks. So always showing you working out is important. I'm sure you're sick of your teachers telling you the same thing, but it is really, really important. So this comes to minus 1,182 minus minus 934 kilojoules per mole. So that's the sum of this bracket up at the top. Now our final answer therefore becomes minus 248 kilojoules per mole. Now this value here tells us it's an exothermic reaction, and it's a relatively large exothermic reaction. So those are the 2 enthalpy of formation calculations we do in this video. I hope that makes sense. I mean, obviously go back and rewind, watch through it again, but it's the same principle every time with enthalpy of formation Hess cycles to calculate the enthalpy of reaction. So let's move on to the enthalpy of combustions. So our first reaction is looking at actually the enthalpy of formation of propane. So this is the enthalpy of formation, but again, I am just going to use the enthalpy of reaction. So I can use combustion enthalpies to calculate the enthalpy of formation of a substance, an organic substance at least, if required to. Now, I'm going to be combusting each of these components, and that means I'm going to produce carbon dioxide gas plus water, and it's complete combustion, so I know I'm going to get these 2 substances. I need to make sure it's balanced. So let's first do the arrows before we look at the balancing. Now I'm going to be burning carbon, graphite, to form carbon dioxide, and I'm going to be burning hydrogen to produce the water. So this arrow here, and again I'm going to call it delta H1, is representative of those 2 combustion enthalpies. You can do the same for the right hand side. That delta H2 is representative of the enthalpy of combustion of propane. Now let's go back and have a look at the balancing. So I need 3 carbons, so that's 3 carbon dioxides, and I need 4 lots of H2, so 8 hydrogens, so I need 4 lots of water. Now I also need to balance up with the oxygen, so I'm going to, again, we saw this in a previous video, putting oxygens on the actual arrow. In this case I need 10 oxygens in total, so I'm going to have 5O2 gas on each of these arrows with plus in front. That's just to keep everything nice and balanced, and like I said on a previous video, you won't always see this, but you have to assume that they are there in order to keep everything balanced. That also means that in order to give me the correct delta H1, I will need to multiply the enthalpy of combustions, or the molar quantities of enthalpy of combustions, by the stoichiometry. So this is the first time we are starting to consider this for combustion and head cycles using combustion enthalpies. We didn't in the previous video, but as above, we need to multiply things up. Now, so at the bottom here, I'm again going to write what delta H1 is equal to. So that is the enthalpy of combustion of carbon. Now it's 3 lots of carbon, so I need to go 3 times, plus 4 lots of the enthalpy of combustion of hydrogen gas. So it's hydrogen gas. Delta H2 is equal to just the enthalpy of combustion of C3H, let's say 3, C3H8, so propane. And we have those values up here. And we'll use those now to construct the description to calculate enthalpy of reaction. So my enthalpy of reaction is as follows. Now, in order to do that, we need to go back to our Hess cycle. We want to start here, and we want to end up here. So I'm going down, just go through that, and up, and I'm going with delta H1, so this is a plus, and I'm going against the enthalpy of delta H2, so this will turn into a minus. So this time, delta H1 comes first, minus delta H2. You can see this is the opposite way around to the formation. So let's input the values and see what we get. So delta HR is equal, now no, delta H1 is equal to this lot over here. So let's open up a big bracket. So 3 times minus 394 plus 4 lots of, let's keep those brackets in there, minus 286. Close those. I want to work this out first. I'm going to show the examiner what I'm doing. Minus my delta H2, which is just quite simply minus 2219. Again, keep all the signs in there, very important. So let's use or get all our kind of numbers in our calculation. So this one here, this large bracket here, totals to minus 2326. Now this minus minus, they turn into a positive, so I can switch that to a positive. And therefore delta HR is equal to minus 107 kilojoules per mole. Now, it's worth just saying at this point, although it's not wholly relevant, is if I was trying to work out for an enthalpy of reaction where I knew the enthalpy was exothermic, and I ended up with a positive sign here, I know I've done something wrong, so I do need to go back through my calculation. This one, not so obvious because of the enthalpy of formation of propane, but it's worth considering if you're asked to work out the enthalpy of reaction. It's a combustion reaction, and you know it's exothermic, and you've got to use enthalpy of formations or other enthalpies to work it out. You know your final answer has to be exothermic, so why not make sure you double check that at the end, keep that in mind, and if it doesn't come out as negative, go back through your calculation and double check. Right, let's move on to the next one. Now, this reaction we have seen before. This is the exact same reaction we did at the start of this video for the reduction of ethene, but we are going to use combustion enthalpies here in order to figure this one out. Now, as in the previous video, I made a point of this and I said it doesn't matter the route we take, as long as our start point and our end point are the same, the enthalpy will be exactly the same. So, and that is Hess's law. The enthalpy of any reaction is independent of the route taken, and hopefully this will prove that that is the case, and hence we'll get exactly the same answer we did at the top. So again, let's have a look at this. This is combustion, so we're going to be combusting each of these components here. So I know I'm going to produce carbon dioxide and water because it's complete combustion. I need to make sure everything is balanced at the top, which it is. I now need to balance my carbon dioxide and water out. I now have 2 carbons, so I want 2 carbon dioxide, and I want 6 hydrogen, so I want 3 H2O at the bottom. Let's draw our arrows going down, because that's the direction we're going to go in. We're combusting these components to produce the carbon dioxide and water. And again, I'm going to write delta H1 and delta H2, just like we had before. Delta H1 is representative of the enthalpies of these components up here, and delta H2 is the enthalpy of combustion of ethane on the right hand side. So again, at the bottom here, I'm going to write out what delta H1 represents, and that represents the enthalpy of combustion. No need to times it by anything because it's only 1 mole within the top equation of ethene, plus the enthalpy of combustion of hydrogen gas. Delta H2, on the other hand, is just the enthalpy of combustion of C2H6, which is ethane. Now, I'm pretty sure throughout all these examples, we've only ever had 1 component for our delta H2. That's not the way it will always be. It's just coincidence that it's worked out for these examples. Now, we now need to calculate our delta HR, which means I need to go to my Hess cycle. I know I'm going to start there and finish there. I'm going to go down, across, and up. A funny arrow, that one. I'm going with delta H1, so this here, don't need to put brackets really, but plus, so that's all of this plus, and I'm going against delta H2, so that's minus, so it'll be all of this minus. So let's have a look at actually calculating our delta HR. I'm just going to write that as I should be writing it, so let's go with delta RH, it's the enthalpy of reaction. What I just wrote before is not wrong, it's just you don't really see it anymore, especially not in the A-level text. So delta HR is, again, it's delta H1, same as the previous example, minus delta H2. Now we have to input our values. The enthalpy of reaction is as follows. Now delta H1 is the enthalpy of combustion of ethene, which is minus 1410.8, plus the enthalpy of combustion of hydrogen, which I've got as minus 286, minus my enthalpy of combustion for ethane, which is quite simply here, as written at the top, minus 155, I believe that is 9.7 kilojoules per mole. Now again, we want to make sure that we work out each of these brackets out so we don't have the risk of losing marks. So our first bracket works out as minus 1696.8. Minus minus makes a plus over here, so I'm just going to switch that to a plus, 1559.7, and our final answer, so the enthalpy of reaction. Now before we actually calculate this, I'm just going to go up to the top and you can calculate this in the meantime, and hopefully we get the right number. So if we just move this to the top to our previous calculation, we should get minus 137.1 kilojoules per mole. In this case, I won't be doing it 3 significant figures, and you need to be mindful of that as we go through the calculations, and especially if it states it in the calculation. The accuracy you need to give this value to, always make sure you do that. A lot of students don't look at that in the question. I haven't put that in my question, so I haven't really been sticking to it. but that's something you really need to make sure you are doing. And conveniently, you may have already worked it out, it does work out as minus 137.1 kilojoules per mole, which again proves the point of enthalpy change for any reaction is independent of the route taken. So in this one, we have gone through combustions, and the very first example we went through formations, but we still got the same answer. That concludes this video. I hope it was useful, and if it was, please hit the like button and subscribe to our channel, and use the comment section to let us know what topics you might want to see next. But thanks for watching, and we'll see you next time.